All right, so we're on worksheet 13, side B. We are not, remember, we're not going to test you on this. This is just an extension of what we have been doing. So it's a nice extension. I would today, though, like to go over these limit pieces so you can kind of understand what they're trying to get at. So the limit of your function as x approaches positive infinity is asking you to look at the far right behavior of your function. So along the far right side here, what value is your function seem to be approaching? Seems to be approaching a 10, yes, and that's exactly how you would answer that question in calc. It's approaching 10. The limit of your function as your x's approach negative infinity, that would be the far left side this time. What value does your function seem to be approaching there?
Still 10.
Also approaching 10. So on the far end behaviors, it's approaching what we know is called a horizontal asymptote. So whenever I ask you for end behavior of your rational function, I could be talking to you about a horizontal asymptote. Now this notation's a little strange. It says the limit of your function as x approaches negative 2, and then they put a little negative symbol in the corner of negative 2. That just means negative 2 from the left side of negative 2. So here's negative 2, and here's the left side of negative 2. Where does it seem to be heading? Towards negative infinity. Very good. But then this little plus sign on negative 2, what do you think they want me to look at now? The right side of negative 2. Or is it approaching this time? Up to positive infinity. Okay, so that particular vertical asymptote has opposite end behavior on it, which means that when I go to write the vertical asymptote factor, it's only going to show up one time in my algebra. Right, because that makes lots of sense. Daniel loves that rule. All right, so then 4 from the left side.
So is that just simply a rule, or is there actually math?
No, there's math reasons for it. Yeah, nothing we want to get into today, but yeah. The mathematical, breakdown of why that happens. It's not horrible. I just don't want to do it today. All right, so for 4, both the left and the right side of 4 of that asymptote, they're both going up to positive infinity. So that tells me when I go to write the factor for that vertical asymptote, we're going to need to see that it shows up twice. Daniel, the simple reason is squaring a negative goes to positive. Okay. All right, so let's try to throw all these clues together into our rational function. And let's start with any x-intercepts that you might see. So I don't know about you guys, but I'm thinking there's an x-intercept right here at negative 5. And I think there's a bouncing 0 at 2. So when I throw that up into this rational function, x-intercepts show up where in my fraction? X-intercepts are in the numerator. So a factor of x plus 5 and a factor of x minus 2. But what else do I have to remember about the factor of x minus 2? It's got to be squared because it's going to not go through the axes. It's going to bounce off. So it has multiplicity of 2. Now let's talk about our vertical asymptotes. I know we have one at x equals negative 2, and it's the opposite one. So we're going to write x plus 2 in the denominator, showing up just once. But what about the vertical asymptote at 4? It's got to have multiplicity because they're both going up to infinity, so squared. So right now, I'm seeing an equal weight rational. You guys follow me? We have a x to the third over x to the third. So we should be seeing a horizontal asymptote that flattens out to some number, which happens to also be my coefficient. It's 10. So I'm just going to throw a big 10 in front of this, and this problem's done. You could put 20 over 2, and then your teacher would be like, yeah, that's 10. Yeah, I got you. All right, number 4. So, interesting. All right, number 4, let's skip the limit on this one because we already did one limit problem. Jeepers, guys. I think it crosses at negative 6 and 6. Are we okay with that? You got young people eyes. Is that what you're seeing? Okay, so 2 x-intercepts. They are going through the axes. So when I write the factors, we're just going to have them show up one time. And then I see a vertical asymptote at x equals negative 2. And another one at x equals 3. But the one that's at 3, I'm seeing that positive behavior. So that factor is going to have to show up twice. So x plus 2 is a vertical asymptote factor. And x minus 3 is as well, but this one has to show up twice. Okay, so what I'm seeing, I think there's a horizontal asymptote there. I'm having a hard time figuring out where it is. I mean, right now we have a bottom heavy rational, which means it would be at 0, and then some people are like, wait, so that one crossed the x-axis. How could it be at 0? Remember, some of those rationals cross through and then they come back up and they kind of scoot along the axes on the negative side of it. So I think we do have a horizontal asymptote at 0, so I think that's fine.
That one goes up.
Yeah, but it goes up and then scoots back down, yeah.
So
It is weird, I'm with you.
that both of them.
Yes, ma'am. Mm-hmm. So there is one more clue in this problem. Do you see it? Mm-hmm. So we're going to be able to figure out the stretch, which does impact where your y-intercept is, so we do need to kind of go through these clues. So here's what I want you to do. Recognize that this is y equals a big mess, and then could you just please, if you're using pencil, just throw like a big K in front of it, which is our stretch, which we're about to find. All right, here's how we're going to find the stretch. We're going to plug in 0 for all the x's and 40 for the y. So I need more room. Where's my extend a page? There we go. Extend. All right, so plugging in what was it, 40 for y? Okay. I don't know k. And of course, I can't remember anything we just did. Was it x plus 6, x minus 6? So 0 plus 6 times 0 minus 6. All over, let's see, 0 plus 2 and 0 plus 3 quantity squared. Oh, yeah. I gotcha. 0 minus 3. Thank you. So could you please figure out what this coefficient of k is? Negative 36 over 18. So is that negative 2? I think so. So we're dividing both sides here by negative 2. And we're finding out that k apparently is a negative 20. Ah, yes, that's exactly what I was going to guess. A negative 20. Not. All right, so then I just go back up here and I go, hey, you know what? K is a negative 20. So that was fun. Not going to be on a test, but don't you wish it was?
Nope.
Not even a little?
Why would I
want that? Now, there will be questions like we warmed up with yesterday where, and you actually already saw one on your no calculator test last week, where it was like, write an equation that has a vertical asymptote and a hole. The next time you see that question, it might be more specific. It might be like, write an equation that has a vertical asymptote at 4 and a hole at 3. And you got to figure out what the factors look like. So it'll be a little more specific, but much less intensive than this, okay? Could you find worksheet 14 and turn to side B? Excellent. That is not the worksheet I thought I had. All right, try again. 14. Oh, apparently I didn't open it. I know, I'm a little slow to this party today. So yesterday we talked about polynomial inequalities, and the only things I had to watch out for were x-intercepts. Well, today we're going to look at rational inequalities. So we have something else to worry about today, because if you think about a rational function, there's other places along a rational function where it might change from positive to negative output. So here's what I mean by that. Ignore this message about taking out worksheet 17 and 15. I don't worry about that today. Okay, so I'm just going to create like the world's ugliest rational function real quick. Yep, that's pretty ugly. Yep, that's pretty ugly too. Now, what if I just looked at that picture and I said, tell me or draw me or highlight or color where your rational function, where this guy is less than 0. Is there any piece of this rational function where it's below the x-axis, where it's negative? Yeah, like here and here. And then is there any place where it's positive? Like here. Are there any x-intercepts in this graph? No, not a single one. So how did it possibly change from a negative to a positive output and back again without having an x-intercept? Well, something is in between those green and red pieces. Vertical asymptotes, okay? So today, not only do you have to worry about x-intercepts changing sign, now you got to worry about vertical asymptotes changing your sign, okay? And you also have to be wary of just because you have a vertical asymptote, it doesn't mean you're changing your sign, because we just saw some examples, remember, where your asymptotes because they had multiplicity on them, they didn't change sign. They were both going to be positive outputs on either side of the asymptote. So there's a lot of generalizations that kids like to make in this lesson, and they're like, oh, it's always going to do this, it's always going to do that. Don't do that, because there's very few generalizations you're going to be able to make with the little knowledge that you guys have on rationals. All right. Could you please, on 14b, you got to write some notes to self, okay? The biggest mistake that kids make on this question, on these questions on the test, is that they don't rewrite it so that the 0 is on the right-hand side of the inequality. So they just look at what I give them, and then they're like, yes, I can totally see where the x-intercepts are. No, you can't. So you have to make sure that everything is moved to the left-hand side of the inequality. And you need, sometimes we call it standard form, but it's really called general form. You need the general form for the rational functions, which means it's a polynomial divided, ooh, that's supposed to be a Q. A polynomial divided by a polynomial. So until it looks like one fraction, you can't talk to me about x-intercepts until it looks like one fraction. That's the big deal today. All right. So let me just walk through this question. This is from your textbook. I know the done question on your notes is like typed up for you, but I know you guys don't like looking at those typings, so we'll look at that one in a minute and highlight some stuff. But first of all, notice the problem from your textbook. It did have everything to one side set equal to 0. So that's great. Just a little note to self, guys. This is the version that I'm going to ask you guys to type on your calculator when we get to that step in our work. Don't go to your new version to type in the calculator. I'll tell you why in a minute. Okay, then, if we're on our homework, you would get common denominators. So this fraction's not too bad. Your common denominator was x minus 6 and an x plus 1. So when they multiplied each fraction by the missing piece, and then they did a little simplification, they got a new version of the rational, and this is what they call general form. This is the version of the rational expression that you guys can answer all those algebra questions about. So we're going to think about critical points. All right, critical points for rationals could be x-intercepts, and then I think Piper just told me they could be vertical asymptotes. So someone remind me, how do you find x-intercepts? Maybe you got to look back at your yellow card if you forgot. How do we find x-intercepts on a rational function? Set the numerator equal to 0. How do you find vertical asymptotes? Set the denominator equal to 0. So basically today is just a fun party of setting things equal to 0 and finding critical points, okay? And just like yesterday, I'm going to have you guys make that number line chart, because that's going to help with our domain intervals significantly, especially for our friends who keep getting those backwards. And we're also going to incorporate the graph, and of course I'm going to incorporate colors, because I'm me and I like to do my math in colors. Alright, so let's take a look at the one that is done on your paper. It's already done for you. The first thing that they did was, it had the equals 0 component to it. Write yourself a little note. This is the version that you would type on your calculator. I always want you to go back to the non-worked on version, because imagine what would happen if you just go type in the one that you get at the end of this problem. What if it's wrong? So like you're convincing yourself that you're right with your wrong answer. So that's not going to work, right? So we got our common denominators, and we combined all of our factors, and we got a new rational. Okay? So this is after they got common denominators. This is the general form, right? That's what we call this, general form. And this allows us to figure out your x-intercepts and your vertical asymptotes. So for x-intercepts, you guys told me I was supposed to take my numerator and set it equal to 0. So they got an x-intercept at 2/3. And for your vertical asymptotes, you would set your denominators equal to 0, and you get 2 vertical asymptotes, one at 4 and one at -1. And this is why I wanted everybody, if you were doing this, to type this version on the calculator. If you type this version on the calculator, you're going to see those exact things if you did it correctly. So if you look at your calculator and you're like, indeed, I do have an x-intercept at 2/3, and I have a vertical asymptote at -1 and at 4. If you typed the original one in and compare it to all your hard algebra work, They should match if you did everything right. I hate when kids type this version in, because if you did a mistake here, you're basing your algebra on your mistake, and you're basing your graph on your mistake. So of course they're going to match. Like, you're doing the same function twice. So I encourage you to not type your new function in. Do one of the original ones, okay? So I know on your paper, they already have what they call a sign chart in your book. The way your book encourages you to do this question is they want you to manually substitute in values, because they're assuming like you're doing this with no calculator around you, which would stink, frankly. But you guys are blessed with the fact that you will be using a calculator when this one comes up. So I don't have you guys plug in numbers because it's a little cumbersome and tedious, because I'm not going to ask you to do this without a calculator. So instead, what we do is we take a peek at our graph, because we already have it in front of us. And if you didn't have a picture of it, you would just sketch a really ugly picture on your paper and you'd bust out the colors. So right here, between negative infinity and negative 1, that function is negative. It's below the x-axis. And then between negative 1 and 2/3, and remember 2/3 was your x-intercept right here, your function was positive. And then after 2/3, it switches back down to negative, referring to where it's located in the coordinate plane, guys, right? Positive meaning above the x-axis and negative meaning below. And then after the next asymptote at 4, it's positive again. So when I go back to the question says, where was your function greater than 0? That's just a fancy way of saying, when was it positive? And it's positive from negative 1 to 2/3 and from 4 to forever. So that's how we'd get the interval, the domain interval, remember, of negative 1 to 2/3 and 4 to infinity. Okay, question. Why did I use all parentheses there and not a single bracket in sight? This? Yeah. Doesn't have what? Doesn't have it equal. Okay, there's no equal to bar underneath the inequality, and therefore I don't consider a bracket in my problem anyways. We're going to, not on a greater than or less than problem. But when we hit one with an equal to bar, which we will in our notes, there's something else that's tricky that we got to talk about. So remind me when we get to that one, we got to talk about it. All right, number 5. So this is the mistake that happens on tests. Kids go, well, you have an x-intercept at 1. Because they go, numerator equal to 0, beep, bop, boop, I'm a robot. Are you allowed to look at numerator equal to 0 yet? No, child, this is not in the right form. It's not even equal to 0. So the first thing I would do is move the 3 over by subtracting it. This is the version that you're going to be referring to when you go on your calculator. But that is not the version I'm going to do my algebra with, okay? So now we're going to get our common denominators to get general form. The good news, though, getting common denominators in these questions is usually incredibly simple. So this one has a common denominator of x plus 2. This fraction already has it, and this fraction needs it. So you're just going to multiply this fraction by x plus 2. So my new general form, let's see, it would be x plus 1. No, it's not. X minus 1. And then you're going to distribute a negative 3. So negative 3x minus 6 all over the denominator of x plus 2. And then we just need to simplify that a little bit, guys. So you got, let's see, negative 2x minus 7 over x plus 2 is greater than 0. This is the version that we're going to do all of our fancy algebra with. It's not really that fancy, though, is it? Talk to me about x-intercepts. You have one. Yep, if you set your numerator equal to 0, you would get, I think it is negative. Negative 7 halves, I'm going to call it negative 3.5. So there's a critical point. And then your vertical asymptote would be when you set your denominator equal to 0. So x equals negative 2 is your vertical asymptote. So here's the catch. If you're doing this little domain line, which I think you guys should do, I really encourage it, you need to put the numbers in the right order. So Yeah, they have to be in number line order. I get kids doing this and they put the numbers down like however they feel, and I'm like, what? Guys, which number comes first?
1.
Out of negative 3.5 and negative 2. Yeah, it's negative 3.5. So keep that in mind, okay? Now, from here, you can either plug in numbers, no thank you, or you could grab your calculator. I love using my calculator because number 1, it's going to confirm all my hard work, which I probably should have done this by now, whoopsies. And number 2, it's going to tell me the positive and negative stuff with a visual interpretation rather than me having to plug in a bunch of numbers. So I need y'all to grab your calculator, and remember, you're not typing in this new version of it. You're typing in this like second version of it where it's x. Everyone please type, guys. X minus 1 over x plus 2 minus 3. Make sure on your calculator you have to put the numerator and the denominator in parentheses because it's got that horizontal script. So you're typing quantity x minus 1 divided by x plus 2 and then minus 3 on worksheet 14b. So y'all told me with algebra that I was supposed to have an x-intercept at negative 3.5. And then we were supposed to have a vertical asymptote at negative 2. Can you confirm visually on your graph that that is exactly what's happening? Otherwise we're going to have problems. We do. Oops, why am I using red? That's going to ruin my thing. Does it look like this? Kind of. I mean, not really, but, you know. Something like this. Wow, that's ugly. Okay. That's like super bad. Let's try this again. That's even bad for me. I could do better. Alright, so here's the good news. I feel like... Okay. I feel like we're on the right track because the things we found with our algebra, I'm seeing confirmed in my graph. So, here's this intercept at negative 3.5. It is negative land until we get to 3. Yes. Alright, and then after that asymptote, we're in negative land again. So, if I kind of add that to my little sign chart here. Now I have to go back to the actual question, because the question was, when is it greater than 0? So they want to know when it was positive. And it's positive from here to here. Now notice I'm not using a bracket at all. You can call it negative 7 halves if you'd like. Why am I not using a bracket on this domain interval anywhere? Because it's not equal to again. So why would I even talk about brackets? Stop talking about brackets, lady. Alright, let's take a look at the next one. Okay, so again, I get kids who look at this on the test on Friday and they go, clearly you have an x-intercept at negative 2. And then I go, oh, child. Are we ready to look at x-intercepts? This is not even the right form. Alright, so first of all, we have to remember that when we're on our calculator, the thing I'm going to type on my calculator is this version, x plus 2 over x minus 4, and then you're going to subtract the 1 over. This is what gets... Go ahead and type that on your calculator while I'm scribbling out some other stuff. Okay? Yes, make sure you have parentheses around the quantity x plus 2 and around the quantity x minus 4. Alright. So, we're going to need to get general form, so we need to get common denominators. Which means this fraction over here is going to have to be multiplied by the common denominator of x minus 4. So you see the common denominator work is not really tricky on these. It's usually just 1 or maybe 2 things you got to multiply. So this piece of it becomes negative x plus 4. When you distribute the negative 1. Oops, that's not the right sign. Someone's cooking their lunch already. Now I'm hungry. Okay. Do you smell that? Oh God, I'm having an aneurysm. What happened? Okay, good. It makes me nervous when you're like, I don't smell that. I don't know, maybe they're burning their lunch. I don't know what's happening. Alright, anyways, look what happens up in your numerator, guys. All you have is a little measly 6. Now, according to our rational function rules, we shouldn't have an x-intercept because 6 can't be 0. So look at your graph. Are you seeing that this one does not have an x-intercept? Okay, good. Do you see a vertical asymptote at 4? Okay, cool. So that's the only critical point that we're going to run into, is that at 4, x equals 4, something happens. So here's where I would most definitely need to borrow a picture from you guys because I have no idea what this looks like. Is this branch down here? Okay. And then this guy's up here, I'm guessing. Whoops, that's ugly. You get the idea. Not that bad. Okay, good. It's not the worst one I've ever done. So the only number in your number line is 4. And on the left side of 4, it's in negative land. And on the right side of 4, it's up here in positive land, right? So I want to know where this rational function is less than or equal to 0. So you're like, finally, we get to use a bracket, I bet, huh? So we know we're not going to use it on infinity, but child, I just put a parenthesis on 4. Why? What happens at 4? It's an asymptote.
Wait, but what if it crosses the asymptote?
It won't cross a vertical asymptote. That's a great question. Because a vertical asymptote is a discontinuity, so it does not exist. It's not defined at that value.
Oh.
So what I do now is on a number line, when I'm worried about brackets and parentheses, anytime an asymptote is marked as a critical point, I put a little star next to it, so that way I remember, even though I want to use a bracket here, I cannot. The interval for which this is negative is from negative infinity to 4 without including 4 because it's a discontinuity. Oh boy, that's a weird rule. And it violates your algebra rule, so it's really confusing. I gotcha. If it was an X-intercept, could we use a bracket? Yes, because the intercepts are 0. That's the whole point of them. All right, let's take a look at number 7. Most definitely not in algebra form. We're not in that general form, but at least this is the form that I'd like to type on my calculator. So can you guys get this version on your calculator, please, while I'm getting some common denominators for us? What do we have here? Leave your denominators always in factored form because you want to be able to see the vertical asymptotes in a minute. Let's see, 4x plus 2. All right. So, according to my work to get the common denominators, and when I use my rational function rules, I'm seeing that you should be seeing one x-intercept at negative 1/2 on your graph. Are you seeing an x-intercept at negative 1/2 or negative 0.5? Okay, cool. And that was from the numerator setting equal to 0, right? That's how we got that? And then the vertical asymptotes are pretty easy to identify when you're in factored form. Are you guys seeing a vertical asymptote at negative 2 and at positive 4? Okay, cool. And if you're not sure, you could always try to trace negative 2, and it should give you like nothing. Error undefined, either on the table or if you're using your actual trace. All right, so on our sign chart, you've got 3 critical values, and you got to put them in the right order. So negative 2, the asymptote would come first, and then negative 1/2 would come next, and then 4 would come after that. And then I'm going to rely on you guys to give me a little insight as to what this picture looks like. But let's see. We've got asymptote, asymptote, intercept. Oh, I think I know what this looks like. Is this first branch down here? Yeah. And then it does a weird squiggly thing here, doesn't it? Like this. Does it do that? Okay. And this branch is up here? Okay. So it looks something like that. So when I look at the function when it's less than negative 2, so on the left side of that vertical asymptote, it's over here in negative land. And then between negative 2 and negative 1/2, it was positive outputs until it hits this x-intercept, and then it switches to negative outputs. That's really ugly, sorry. And then this other branch after the asymptote is positive the whole time. So when I kind of add that up to my sign chart here, we got negative, positive, negative, and positive again. So when I actually go look at the question, they want to know where your rational is greater than 0. So I'm asking where the rational is positive, and you'll notice when I throw some brackets and parentheses looking things on my sign chart, I'm using all parentheses this time because there's no equal to, so we're not worried about that. All right, so -2 to -1/2, it's positive, and it's also positive from 4 to infinity. Okay, so you see what I mean by like the little number line really does help with domain because you just read it off in left to right order. It's kind of nice. I like it. Well, you know the last one's going to be the worst one, right? Like that's usually how this goes in math. The last one is the most fun, I should say, not the worst. So I get kids who look at this and they go, well, clearly there's an x-intercept at -1/2. And you tell that kid, no, not ready for that yet. All right. However, you are totally ready to type on the calculator once you get this in the proper form. So please practice typing this on your calculator. I want every soul in here remembering that you have numerators and denominators that need to be grouped in parentheses. And then you're going to add the 1 over. Oops, that is not the right sign. Add the 1 over before you say greater than or equal to 0. This is the version that I want to see on your calculator. All right, I am going to work on getting us common denominators. That's not too bad. We just need a 3x minus 2, right? All right, so let's see here. I was going to take a shortcut, but I think this is not a good moment to take a shortcut, so I'm not going to. (5x minus 1) over 3x minus 2 is greater than or equal to 0. So this general form of my rational, it's telling me that you guys should be seeing 1 x-intercept and 1 vertical asymptote. You seeing that on your graph? Oh, good. So your x-intercept, algebraically, it's found by taking your numerator and setting it equal to 0. So you should be getting an x-intercept at 1/5 or 0.2. You can test that out using your trace feature. Vertical asymptote, of course, is your denominator equal to 0. So do you see a vertical asymptote at 2/3? X equals 2/3? Okay, good. All right, so a little chart. And this time, because we have the equal to bar, I'm a little worried about the bracket situation. So here's what I'm going to do. I'm going to put my numbers in number line order. So the 1/5 comes first. When it's the asymptote, I'm going to put a little star next to it. And I'm going to write a little note to myself that 2/3 is an asymptote. So when I hit the asymptote on the number line, I have to remember that it can't be 0. It's a domain interruption, okay? It's a discontinuity. So I can't use a bracket on an asymptote ever. When you guys look at your graph, oh boy. I'm really not sure I know what this guy looks like. 1/5, 2/3. Does it look like this? Something like that? Okay, cool. All right, so we've got positive outputs until it hits the intercept, and then negative outputs after the intercept until it hits the vertical asymptote, where it switches back to positive outputs after it. So according to my inequality, I'm looking for places where this function is greater than or equal to 0. So, boom, and then I'm going to use a bracket on the 1/5. But notice what I'm doing on the 2/3. Why did I use a bracket on the 1/5 but not on the 2/3? 2/3 is an asymptote, 1/5 is an intercept. Intercepts can totally come out to 0, so you can use a bracket. Asymptotes cannot. So your domain interval starts at -infinity, goes to 1/5, including the 1/5, and then it jumps to 2/3, not including to 2/3 though, and then continues on forever. That is a stinker of a question. Whew. So here's the good news. Oh my goodness, guys, you guys have like time to work on your homework. Your homework is the rest of worksheet 15A. So remember last night for homework, you did numbers 1 through 5. And now you're going to do numbers 6 through 10. That's going to be your homework tonight, okay? So right now, instead of packing everything up and talking to your neighbor, you can maybe get a couple of problems done from your homework assignment.